What if you could take 3D Scratch games to the next level? Imagine being able to make VR games in Scratch. In this video, we'll do exactly that. Welcome to the third and maybe final devlog, where after a whole year of development, we will make and complete a VR game. If you haven't seen the previous two devlogs, you should totally go check them out, but there isn't too much important information you'll need to know beforehand for this video. So, let's get started. Currently, we're working on making a VR platformer, where you move in the direction you look. In fact, this is somewhat of a complete game. Your goal is to utilize the jump pads to get to the end without falling off. But this game needs to be trashed. Okay, I guess it doesn't need to be scrapped, but it really should be. To understand why, we need to go back to devlog 1. Oh man, that was so long ago. And take a look at this comment. This comment goes into detail about why there aren't a lot of VR platformers. The reason? Because it can make your players sick. I'm assuming they're referring to motion sickness. Motion sickness occurs when your body is moving but your senses think otherwise, or vice versa. For example, this may happen to you when reading in a car or playing an immersive racing game. Back to the platformer, what we're doing is causing our visual senses to think we're moving, when we're actually standing quite still in real life, resulting in an easy way to cause motion sickness. Our goal then should be to reduce motion sickness in a platformer, but the whole concept of a platformer requires that our players should move. While there are other ways to simulate movement in VR, none of them seem viable for a Scratch game, as they usually require hardware Scratch really doesn't support. Unfortunately, this means that the whole platformer concept has to be scrapped. That being said, I'm actually kind of glad, because even after making our game VR, this platformer still felt kind of generic. However, we now have to make a new game. In order to properly discuss this game's development, we're going to need an organization system for this video. I will divide this video into 3 sections. First, graphics, and then gameplay, and then finally, miscellaneous improvements. Now, you might be wondering, why prioritize graphics over gameplay? From what I've learned about game design, it really should be the other way around. But graphics is what I would call the major limiting factor of our game. You see, the prerequisite tool for 3D Scratch games is the pen tool, which is quite slow when it comes to 3D. Too many pen drawings and we can end up dropping the frame rate. Therefore, our game has to be designed with graphics first in mind so that we don't overdo the graphics and create a game with a slow frame rate. With that being said, let's dive into the graphics section. So, what are we trying to do with this VR game? Well, let's break it down. We're trying to make a 3D VR game in Scratch. We want our game to run at the max frame rate, 30 FPS on native Scratch, to make sure our players have a smooth experience. Speaking of native Scratch, that's where we're going to need to run our game alongside Turbo Warp, and we need to run it on phones, which is lower end hardware. Oh, and as a comment from Random Studios pointed out, we need this game to look realistic to create a true VR experience. And speaking of VR, we need to draw everything twice. Yeah, from what I know about 3D and Scratch, this would be nearly impossible. From what it seems like, we're going to have to make some sacrifices, and it seems like this sacrifice will probably have to be the realistic factor. Realistic games in Scratch usually require lots of pen drawings that usually necessitate Turbo Warp or other mods. But other than that, I think this might be possible, so let's go! This is probably a good time to get a better understanding of how slow the pen tool is. According to the sample script I created, my computer can draw over 100,000 lines a second, or a little over 3,000 lines a frame at 30 frames per second. That may seem like a lot, but wait, we're making this game for a phone, not a computer. Obviously, this iPhone won't be able to draw as many—
300,000? What in the world?
Yeah, so I did not expect that. I found this out when writing up my script, and I just think it's crazy. 300,000 lines a second, or 10,000 every frame. Wow. But why did this happen? Now, I don't want to get too into detail since we are at the start of the video, but this is a good time to go to good old ChatGPT. Well, there are several reasons why my computer could be performing worse than an iPhone. The one that seems the most connected to this issue is how these two devices handle rendering. My computer, with its GTX GPU, uses immediate mode rendering, whereas the iPhone uses tile-based deferred rendering. Basically, this difference in rendering allows the iPhone to outperform my computer when drawing many pen lines at once. Don't worry, I don't fully understand this either, and I also didn't want to get into too much detail because I didn't want to sound like ChatGPT was talking through me. But if you want to learn more, I'll put some links in the description. Technical stuff aside, this is a crazy discovery, but now I know what to improve if I ever try another VR project. But for now, let's get into this game's development. My first game idea is some sort of snowball fight game. Your goal is to throw snowballs at oncoming enemies who are trying to throw snowballs at you. I've had this idea for a while now, but to make it in VR would be crazy. The first step of making this game's graphics is to create the trees that the enemies will hide around. We can create a tree simply by drawing a line for the trunk and a dot for the canopy. Yes, I took some inspiration from Chromecat's 3D Funhouse. There's just one problem. See if you can figure it out. Did you catch it? Right here, our tree on the left screen is overlapping into the right screen. This is not the intended behavior. What is the intended behavior is to cut off the dot at this line. But how do you do that? After some coding, I eventually came up with this circle drawer that does the trick. The problem is, this circle is usually made up of 360 lines. That is too many lines, at least enough to make my computer lag whenever it needed to draw said circle. After some consideration, I realized that this just wouldn't work, so it's back to the drawing board. So here's likely what happened while trying to decide on the next game idea. I was playing, okay, I'm probably gonna botch this pronunciation, but Yenye? That's what Translate says. Anyway, I was playing their Vectoid 3D tower defense game for inspiration purposes, and that's when I was like, hold up, why not try to make a game similar to this in VR Scratch? How it would work is instead of placing towers to destroy enemies, you would be upon the only tower and you would have the mission of destroying all the enemies. While multiple towers is a major part of tower defense games, trying to destroy your enemies yourself still sounds like a lot of fun. So, in the typical fashion, I got to work making a VR tower defense game even though I have barely any concept of what a tower defense game really is. Most of what I know comes from Scratch games. First things first, I removed all the boxes in the game and placed one right underneath the player. Next, I gave the player the ability to launch projectiles, which definitely caused some lag. Maybe the projectiles shouldn't be cubes? Next, I drew in another box for enemies to come to our base. After that, I drew in an enemy, which prompted another issue, object sorting. Notice this weird overlap happening here? Yeah, that's because we aren't sorting our lines, so the lines farther away in 3D are being drawn over the lines closer in 3D. My first approach to solve this was to sort each object drawn on screen, but then I realized it was much more convenient for this game to sort line by line. To do this, we describe each line with a couple of lists, where each list describes one property of the line, with one of these properties being the average distance the line is from the camera. Rather than sorting each one of these lists by distances, we can speed up the process by creating one more list, the indexes of each item in the list. In other words, it's just a list of numbers up until the list length. Now, if you sort the list of indexes by the list containing the distances, you can then go through the list of indexes, technically backwards, and each index will give you the index of the next item to draw. And that's basically it. But wait, how do you sort a list in Scratch? Well, I made a video on that. And thanks to Jim for noticing a bug with the code. And there we go. After we have implemented object sorting, we can now create drafts for not 1, not 2, not 3, but 4 different enemy designs. Although yes, one of them is just a dot. Our next task is text. In this game, we're going to need to display text for health, the wave we're on, and our upgrade levels. I could have used one of the many 3D text engines out there, but I ended up creating my own. Originally, I used an if chain to determine which letter was being written and then where to draw the lines on the screen. While this worked out great, it did annoyingly slow down the editor whenever the render sprite was open. Therefore, I realized I needed to switch to a more condensed method. So I opted to place all the letter draw data inside of a list, where each item in the list represents a letter. I separated each of the line data with delimiters, or separators. So a pipe would separate different lines, a semicolon would separate the y and x values for the lines, and a comma would separate between the first y and x value and the second. Not only did using a list speed up my editor, but it allowed me to easily implement text rotation rather than manually adjusting each draw block. The only drawback is that I believe the list method did introduce some computational lag, but other than that, it worked out well. After creating some text, I started on the upgrade board, but looking at our current game, the background's pretty boring. So let's add some particles, giving our game a space feel. Of course, each one of these particles is one use of the pen, which means that these particles can easily slow down, well, my computer. Also, due to the quality restriction of the pen tool, it doesn't look as cool as running it through TurboWarp with high quality pen enabled. Therefore, I didn't want the particles to appear unless I was running this game through TurboWarp or a Scratch compiler. To do this, I utilized a custom boolean called isCompiled, which can be created simply by creating a custom block with said boolean saving the boolean, and then deleting the custom block definition. Scratch will automatically default this boolean to 0 or false since it's outside of the custom block. However, when TurboWarp or any other Scratch compiler runs this program, it will change the block definition to true. After utilizing this trick on our particles, let's now switch to the upgrade board. This board will list all the available upgrades in our game, as well as some important information that we'll cover later in the gameplay section. To frame our 3x3 wall, I originally thought about using squares, but a square costs 4 lines, and that would mean 9 times 4 or 36 lines, not to mention the inefficient line overlap that would exist. So I decided on a simpler design of a tic-tac-toe board that only costs 4 lines. Next comes drawing the text. Now, as I mentioned earlier, I believe that the list method for storing text data did have a computational drawback. When I tried drawing every piece of text on the upgrade board, the FPS counter dropped to 15 FPS, even when not looking at the board, meaning that this drop is not caused by graphics lag. To solve this dilemma, I only drew the upgrade text that the player was currently looking at. This also helped as now the player knew, well, what the player was looking at, as sometimes the blue dot indicator doesn't line up with what the upgrade wall thinks the player is looking at. But wait, where did the blue dot come from, and how does it go where the player is looking at? To answer this question, we're gonna need some trigonometry. So as you can tell, the blue dot appears when we look at the upgrade board or anything near there and indicates the focus of the player's eyes. But determining this focus can be a little tricky. For simplification purposes, let's say that our player coordinates are at the origin, or 0, 0, 0. The wall is located alongside the z coordinate of 50, so we can set the z coordinate of the blue indicator to 50 as well. Now, to calculate the x coordinate of the blue dot, we form a triangle with the bottom side being 50 minus 0, or 50. The bottom angle being our player's rotation on the x-axis, and the left side being the x-coordinate of the blue dot minus 0, or just the x-coordinate. Now, there's a math formula that says that the tangent of this angle is equivalent to the length of the angle's opposite side divided by the length of the angle's adjacent side. If you don't know what tangent is, don't worry, this right here is the main definition. But even then, just know that it's a function available in Scratch. Anyway, all we need to do is multiply both sides by 50, and there we go. This will now give us the x position of the blue indicator. However, since our player's x position is not at 0, we just need to add the player's true x position to the final value. To solve for the y position, we can replace the player's x rotation with the player's y rotation, and the player's x position with the player's y position. And there's how we calculate the blue focus indicator's position. Now, where were we? Ah, yes, the upgrade board. After finishing the upgrade board structure and text, I added a health indicator, a waves indicator, and these 5 numbers that we'll cover in gameplay. Don't worry, we're not too far from the gameplay section. It will begin about now. I've only been talking about different bits and pieces of the game, so let's go into depth about how this game will work. This game has 7 different enemies to battle, coming in 4 types: regular enemies, fighting enemies, frozen enemies, and burning enemies. If the enemy reaches your base, you lose health based on how much health remaining the enemy has. But if you successfully destroy the enemy, you gain coins. These coins can be used to buy 7 different upgrades: reload, damage, protection, blast, monetary, burn, and freeze. Upgrades become more essential as the game progresses, but you can only apply up to 10 upgrades per 1 blaster. Don't fear though, you get 5 different blasters in this game, which correspond to the 5 numbers here. Enemies come in waves, and there's a total of 40 waves to conquer until you successfully win. So, let's program this. After creating the data for the enemies, my first goal was to make them move. Now, they are coming slowly but surely to the base, so we better stop them by utilizing our projectiles. But first, we need to determine when our projectiles, which are spheres now, collide with the enemies, which have cube hitboxes. Now, I do have to admit that I used ChatGPT to help me solve sphere-cube collision, as well as in some other places. I figured that since I probably would have looked up how to do the code anyway, it was fine to use this resource. I know this will probably get varied reactions, so this could make a great comment discussion, maybe? I mean, with the creative learning assistant. After implementing collision detection between a sphere and a cube, I realized that if a hitbox is small, the sphere can warp through the hitbox. So instead, I opted in for collision between a line segment and a cube, where the line was formed by the point the sphere currently is and previously was the last frame. This solves the problem of skipping through the hitbox, as the line would hit the hitbox anyway. However, how do you detect collision between a line segment and a cube? I used ChatGPT again, but if we're going to use this code, we probably should get a good understanding of how slab method collision detection works. This one's gonna be long, so let's get started. In order to understand how collision between a line segment and a cube works, we need to think about our line differently. Let's pretend we're drawing our line over time. So at time 0, we're at the beginning of the line, and at time 1, we're at the end of the line. All the other time t's in between 0 and 1 reference all the other points on this line. This can be kind of confusing. Note that this time isn't related to time in real life or in-game time. It's just a way of thinking about our line. In fact, you can call this way of thinking parametric. Now that we know how to reference our line, we need to do some calculations on each axis. For this example, let's focus on the x-axis. First of all, we need to remove the bounds on our line segment so this line goes out to infinity. Now we need to determine what time t our line enters the box and when it exits the box on the x-axis. This may not occur for a line segment that may fall short of entering or exiting the box, but it is guaranteed for a true line that goes out to infinity, with one exception we'll cover soon. To calculate when the line enters and exits, we'll use two formulas which are displayed on screen. The smaller of these two values is when the line enters, and the larger of these two values is when the line exits. Therefore, we keep these two values in store for later, and do the same thing on the y and z axis. But wait, there's an exception we must cover. If the line is parallel to the axis, then one of two situations must occur. If the line is inside of the box, then, at least according to this axis, the line is always inside the box, meaning it doesn't matter when it enters or exits. If the line is outside of the box, however, then it is impossible for the line to enter the box for this axis, and thus it is impossible for the collision to occur across all three axes. With the exception out of the way, let's take the entry and exit time values for all three axes. In this example, we'll assume we have values for all three axes, but you might only get two if the exception applies. Now, all we need to do is to determine if there's a time t where the point at that time is inside the box. If there is, then the line must collide with the box. To find this out, all we need to do is to make sure all of the exit time values are larger than all of the entry values. If so, then that time t must exist. Now, if one entry value is greater than one of the exit values, that means the line exits the box on one axis before it enters the box on another, meaning that the collision cannot happen. To calculate if all the exit time values are greater than all the entry values, we take the maximum of the entry values and then the minimum of the exit values. If the minimum is greater than the max, then the collision occurred. If not, then it did not occur. But wait a minute. If you've been paying very close attention, you may have noticed that we stretched out our line into infinity, but we haven't taken into account the fact that we're dealing with a line segment, not a line. Since our line segment begins at t equals 0 and ends at t equals 1, all we need to do is add 0 as a value to the entry values and 1 as a value to the exit values. And there we go. Whew, that was a lot. The important thing is that we got the code. Here it is if you want to take a look. Now that we have collision created, we can now destroy enemies on impact, but these enemies shouldn't be able to take only one hit. Thus, I created enemy health, as well as a progress bar that my friends were quick to note was going the wrong way. Don't worry, I'll fix that later. After enemy health comes player health. If an enemy reaches the player's base, it will dish out 1-to-1 the health it has remaining. Around this time, I also took a note from the comment by Random Studios, which said that I should prepare my game to run at higher frame rates for the Turbo Warp version of this project. In order to do this, we need to implement delta timing. But wait, what is delta timing? You see, Scratch runs games at 30 FPS. While this is a nice speed, it's not exactly smooth, which is an important property of a VR game. If the motion isn't smooth, that can lead to motion sickness, seizures, and a lot of other fun stuff. Unfortunately, Scratch's frame rate is maxed at 30 FPS. However, when running games through Turbo Warp, we can change the frame rate max to whatever we want, up to 250 frames per second, but with one catch. As we change the frame rate, the game's speed changes along with it. So playing at 60 FPS would double the speed of our game. However, we can keep the game's speed consistent by using delta timing, which you probably already know if you've created games, especially in game engines. You see, we can create a variable called delta time, which tracks how much time we've waited from the previous frame to the current frame, utilizing days since 2000. A small delta time means that we're running at a high FPS, but a large delta time means that our FPS is dropping. Now, if we multiply any movement in our game by delta time and then another constant such as 30, we can have the movement of our sprites adjust with the frames per second count. At high FPS, where the delta time is low, the objects move less than normal. At a low FPS, where the delta time is high, the objects move more than normal. This will not only account for any manual FPS changes, but also if our game lags, so the game moves at a normal speed no matter what. And that's delta timing, so let's implement it and get back to the game. Our game currently only has one wave, so I created a system that introduces our enemies in multiple waves. Now our game is starting to take shape, but there's one problem. It's getting difficult rather quickly. To fix this, we're going to need to make our first upgrade, reload. Currently, you can only fire one projectile every second, so reload will give you the ability to decrease that wait time. To calculate the cost of each reload level, as well as how much wait time each reload level has, we use exponents. Of course, if you ever needed exponents in Scratch, you know that they can be difficult since there is no exponent block in Scratch. In this case, however, exponents can be recreated using some algebra. After implementing the reload upgrade, I decided it would be reasonable to implement the damage upgrade, which increases the damage your projectiles do to enemies. And after implementing the first two upgrades, our player is now ready to fight some more enemies. Our third enemy is a fearsome enemy. It shoots projectiles right at you. If you get hit, you aren't able to shoot for a period of time. This can be dangerous, as a chain of these enemies can prevent you from shooting at all, immediately costing you the game. So we need a few ways to defend against this enemy. One way is by simply shooting projectiles. If the two projectiles collide, they will destroy each other. Pro tip, a high level of reload is good to prioritize, as it can definitely help with fighting this enemy. The other way is by the protection upgrade, which can reduce the amount of time you are unable to shoot to a fraction of a second. After this third enemy comes our fourth enemy, which isn't pretty bad other than that it's fast and has 30 health. At this point though, our upgrades are starting to get a little expensive. So you know what to do? Let's create an upgrade to fix that. This upgrade is called monetary. Yes, it's a bit weirdly named, but I thought it'd be fun to name it that way. Different levels of monetary can either double, triple, quadruple, or quintuple the amount of coins you receive from enemies. While quintupling your coin payment may sound like fun, note that it will first cost you a total of 850 coins to achieve the upgrade, and you will only be able to upgrade 6 more times for that blaster. Actually, it doesn't sound half bad. Alongside monetary comes our last regular upgrade, blast. Whenever you shoot an enemy, the blast level affects how much damage close by enemies receive. It doesn't do too much damage, but it does make a difference on large waves. Now that we have 4 enemies and 5 different upgrades, it's time to implement 2 special enemies, frozen and burning enemies. I first implemented the frozen enemy and its corresponding upgrade, burn. In order to destroy this enemy, you first have to unfreeze it using the burn upgrade. After that, I implemented the burning enemy with its corresponding upgrade, freeze, and the enemy cannot be destroyed until it is cooled down. Now, if you think about it, it wouldn't make sense for a projectile to have both the burn and the freeze upgrade, so only one can be applied per blaster. However, this requires we add support for switching blasters, so let's add that in. After that, we can now apply the burn upgrade to one blaster in order to destroy a frozen enemy, and also apply the freeze upgrade to another blaster in order to destroy a burning enemy. However, it is a little bit difficult to switch between blasters, so you do have to play this strategically. My friend suggested I created a way to switch between blasters using the scroll wheel, which I also implemented. After that, our game is almost done. I think we should add one more enemy, and then some finishing touches. This 7th enemy not only travels fast and has 40 HP, but it also shoots projectiles at you. If you don't do any damage to a chain of 3 of these enemies, they will deal out 120 health points, which is enough to kill you on easy mode. After implementing our last enemy, we only have a few things left to do. We first need a way to lose the game, rather than having the health go down into the negatives. So I stopped the health once it reaches 0 and slowly faded the screen to indicate that the game was lost. Now, losing is no fun, so we also need a way to win. I utilized a bounce script I found from a tutorial project and applied it to the text. And there we go. Now our game will finish properly. After this comes one last change, sound. I want the sound of this game to be a little more special and utilize spatial audio. Now, spatial audio can be a really complex topic, and we're not going to get into the complexities other than panning and volume, but here we go. So if you think about it, in a 3D game, especially in first person, farther away objects should sound quieter than close objects, and if you have headphones on, you can pan the audio to one side or the other based on which ear is hearing more of the audio. In order to do this, I first created a special sound sprite for any sounds that would need spatial audio applied. Then I created a broadcast for any sprites that wanted to issue sounds, so I'd place the sound and the position of the sound inside of some variables and then send that to the sound sprite. This does create a problem though, and that is if 2 sounds play at the same time, one sound will override the other, but that is okay for this game's purposes. Now, once the sound sprite receives it, all it needs to do is some calculations of how far away it is and where it should pan the audio, and then it can play the sound. And there we go. Now we have some sound as well as some music in our game that adds a little bit more life. After that comes a few minor changes. For example, I also worked on a main menu system I created earlier to provide computer, mobile, and VR support for this game. I also changed the method of looking around to utilize the mouse or touchscreen instead of the keyboard. And there we go! We've now finished the major gameplay as well as some other improvements such as the main menu system. Our game is now starting to take form, so let's head over to miscellaneous improvements. Now, after all this discussion about making a 3D game, you may have forgotten about our end goal: to make a VR game in Scratch. Now, for this game, we're going to need rotation sensing to determine what we're looking at and the controller that can map to the spacebar for our game. In the last video, we figured out some solutions for both native and modded Scratch. Well, that's what I thought. So after releasing this video, I was on vacation when I was thinking to myself about a particular comment. This comment had a great idea. We can take some sort of circular object that has color, such as a ping pong ball, and attach it to a makeshift controller. Then, if we use video sensing to get this ball's 2D position and size in Scratch, we can transfer that information into a 3D world, meaning that we'd be able to get the 3D position of these controllers. If we're looking straight out into the distance, the X and Y of the ping pong ball would tell us the X and Y in 3D of the controller, and the size of the ping pong ball would tell us the controller's Z position. This is an amazing solution. Why didn't I hurt this? However, when I've seen Scratch use video sensing, it always uses the front camera. Therefore, in order to make this work, we're going to need two phones, one in the headset and one on the opposite side of the headset, which tracks the positions of the ping pong balls. This latter phone would send information via cloud variables. But wait a minute, I just remembered something. I believe that when you turn on video sensing in Scratch, Scratch will turn off cloud variables as well. This is a safety measure, so nobody tries scanning your face and then sending that information to their own servers or something. But wait a minute, that's what we're currently doing with our native Scratch approach. We're using video sensing to get rotation information and cloud variables to get controller information. While both of these solutions work great, once you put them together, they conflict with each other. This means we're probably going to need another solution for controllers in native Scratch. I was thinking about a different controller option and decided to settle on the Makey Makey. Originally, I ignored this option because of wires. Yes, this can be kind of annoying to connect to a phone that's already inside of a headset, but it can be done. Unfortunately, when I tried to plug this into the Android, it just didn't work. I believe this is because the phone doesn't have on-the-go support. However, if this phone did have on-the-go support, we can probably then use the Makey Makey. But I can't test this. However, this does mean that the Makey Makey is probably a valid solution. Therefore, I think it boils down to a weird option: a Bluetooth keyboard. While I'd prefer to use a regular controller, every time I've tested this VR game, I've used a folding Bluetooth keyboard that I have, and it works great. It doesn't have the controller feel, but I think this is what I'm gonna settle on for now. Now, we have one last task: creating the headset for native Scratch. Since we have to use the front-facing camera for rotation detection, we need to create our own headset that allows us to access this camera. I found some instructions and it was pretty straightforward. Now, to be honest, this was very tricky to get working. I had the battle accidentally adjusting the screen, accidentally pressing buttons on the phone, and getting myself into the position where Scratch VR could work. But eventually, I was able to get it to work. Unfortunately, I didn't have the best experience. My biggest problem was that since I used a DIY headset, I didn't use any lenses, which is definitely necessary for a VR experience. I also did encounter drift with video sensing. However, I was able to complete 2 waves and get an upgrade, so it's definitely possible. But if you try this, seriously, use lenses. And, to be honest, I think this should be the stopping point when it comes to improvements. You guys have some amazing suggestions that we could further apply to this project, such as utilizing full screen, gamepad, and 3D extensions. However, I'm not gonna lie, since I've been working on this project for a while now, I'm gonna go crazy if I don't switch to a different project soon. But that being said, this has been one of my favorite projects and I don't regret a single minute of it. It was a lot of fun making this game, especially getting your suggestions. This video is dedicated to the viewers of the first 2 devlogs, who skipped to the end of the video hoping to find a complete VR game, only to find a cliffhanger. Well, my friends, let cliffhangers be no more. Now is the time to show you the complete VR game. Okay, so that was actually footage of me playing the game on my computer. So here's some footage of me playing in VR. While this is rolling, I do want to say some final comments. First, where to find the game. The native Scratch version is on Scratch, and I have the modded version as a web page and as an SP3 file for download, all of which is located in a description. Also, I would love to talk about what I would do to improve this game if I had more time. For one, this game is very rigid. There's not many smooth animations that most good Scratch games usually exhibit. That's probably the #1 thing I would fix, but I'm still happy about this game otherwise. Of course, also improving the VR experience would be the other major thing I would focus on as well. As Random Studios once again pointed out, it's really important to have a realistic 3D experience in VR. So at least I wanted to utilize the 3D extension in Turbo War. And finally, this game needs more enemies, more waves. That would be awesome to add. Finally, thank you all for watching. This was a lot of fun to make. I'm not sure if I'll make a 4th devlog or a VR Scratch tutorial, but I'm definitely hoping to take a break from VR and focus on some other Scratch ideas that I have. Anyway, that being said, I hope you enjoyed the VR series. Okay, fine. I need to make one more improvement. We need to make the lines glow so the thumbnail looks cool. Ooh.